Okay, here we're going to do some example about the torque and angular momentum. The first problem over here is like a bio-related problem, which you see a person with a leg, and he kicked his leg by giving a force. So that force is 2,000 Newton. This force is the force that will try to pull his leg to kick. So this force over here is 2,000 Newton. Now this force is provided by a muscle, and then we didn't show the muscle here, but that's going to be, you're going to have a muscle try to pull it up such that the leg will kick to the front. It also tells you this force with respect to the bone where it connects to is 2.2 centimeter. So this R here represent what? It represents our lever arm. And that's 2.2 centimeter. It's very small, and that's how the design of our leg is. It's not going to give you a lot of room. And therefore the muscle is going to provide larger enough force in order to make your leg kick. If the leg is heavier, then you certainly need larger force, try to make it move. But here, since we are looking at this motion is not purely just a linear motion, it is actually a rotation, right? We have the center of the rotation around here, and your leg is going to go this way to do the motion. So this is actually a rotation problem. And where is the rotation is generated? How does things will start to rotate? If you want to make things rotate, then you have to provide a torque. So this problem is a torque problem, and you need to give a force, you need to give a torque in order to give the rotation. Okay, now they give you the moment of inertia of the leg, which because this is not like a regular shape, so to do this calculation is not possible. Just simply give you the dimension; it will be too complicated. But this number is given to you. We want to find what is the angular acceleration of the leg. So the first question asking about angular acceleration. Then you have to ask yourself, what is the angular acceleration to do the force over here? As a matter of fact, the angular acceleration is related to torque, not to the force. So let me just kind of give you a quick review. So if you have a linear motion, and this is based on the Newton's second law. The Newton's second law tells you if you give a force, then you will make it an object with a mass to generate a linear acceleration. So you'll accelerate, the direction of acceleration is the same as your force. And if you have a rotational motion, then you need a torque. The torque is also a vector, and this vector is going to make something start to rotate. And as opposed to the linear acceleration, this is going to have an angular acceleration. Alpha represents angular acceleration. And this is not related to the mass. This is related to this one here, which is a moment of inertia or rotational inertia. So what we were given is a force, but you know from the definition of the torque itself is equal to the force perpendicular times the r, which is the distance. Or it can be also equal to r multiplied with the r perpendicular multiplied with the force. More generally, you can just simply write, the distance and also multiply with the force. Then you multiply with the cosine angle. If you have an angle between the force and also the distance, the direction of the pivot, this should be the sine angles instead of the cosine angle here. So this angle is the angle between the R and also the F. And so let's look at this one here. Do we have enough information? Now we are given with 2000, that is force. And we also give a lever arm, that is our R. And this R, because it's a lever arm, is actually a perpendicular one. So you are given with this number, 2.20 centimeter. This one is 2000 Newton. So we got enough information to find out the torque. So therefore, my torque over here is going to be 0.022 meter multiplied with 2000 Newton. Okay, so just try to make the unit to be consistent. And if you multiply this together, then you're going to get 44 Newton times meter. And that's the unit for a torque. Okay, so that is what the torque is. You also need to know that if you apply a force in that direction and your point of the rotation is over here, then what is the direction of the rotation? Now you can use your right hand by making a direction of the R, then make the rest of the finger goes to the direction of the force, and you should know if you do that, the direction of the rotation is going to be counterclockwise. And if you use your right hand, then you do that to find out how this thing is rotate. Your thumb will point outward of the paper or the outward of the screen, and that tells you this is a positive. So this is actually a counterclockwise rotation. But we are not trying to find tau. We are not trying to find the torque. We try to find the acceleration of the lag. And then you can use this equation to find that. So the acceleration is alpha. So alpha is going to be equal to my tau over my I, where I is given. So this is simply just 44 Newton times meter divided by 1.25 kg times meter squared. And that is your angular acceleration. That will give you 35.2. And the unit for this is the radian per second squared. Okay, so that's our angular acceleration. The second part of the question asking about the rotational kinetic energy. After it go through certain angle, so how do we find out the energy of this? How do we find out that? Well, if you want to find the rotational kinetic energy, so what is the rotational kinetic energy is? So let's remember that we talked about this in the previous lecture. We have a kinetic energy for the translational, and the translational is 1/2 mv square, where the v is the tangential direction speed. You also have a kinetic energy of the rotation. That's 1/2 I omega squared. And so the question becomes, how do I know if, because this is the equation, how do I know I? Well, I is given 1.25. Now, the next question is, what is omega? What is the omega after the lag is being rotated to a certain degree. Okay, so how do we find that? How do we find omega? Well, so when you give a force, you're gonna get the lag start to have angular acceleration. That's assume this movement is going to be a constant acceleration motion. This is a constant acceleration and rotation, which means this one is a constant. And what is the constant equal to? That's equal to 35.2. With this information, how can we find omega? How do we find angular speed? Well, constant acceleration motion, you have three equations you can use. Similar to the linear motion, we have one equation look like this. The final omega is going to be initial omega plus the acceleration times the time. We also have this equation, which is the change of the angle plus the initial angular speed times the time plus 1/2 alpha t squared. We have third equation, which is this equation, omega f squared equal to omega 0 squared plus 2 alpha and theta f minus theta 0. So which equation that we should use? That's based on the unit that you have. That's based on what kind of information that you have. Now we have the information of alpha, so we don't have any information about the time. So certainly you're not going to use the second equation. You're not going to use the first equation as well because there's no time information that is given in this problem. So we will use the third equation. Now, when you use the third equation, initially we assume there's lag is not moving, so there's no omega 0. We just need to know what is the final omega square that is equal to 2 alpha times the change of the angle. What is the change of the angle? Well, it tells you it's 57.3. And it's degree, but when you do this calculation, since alpha is in radius, so this one should also use the radius. So that's equal to 1 radius. And therefore, I can write this one, omega f squared, is simply give you 2 times 35.2 radian per second squared times 1 radius. And that's simply just 70.4. And you want to find a final velocity that omega f is simply just equal to the square root of that. And that will give you the speed of that. So let me just do a quick calculation, 70.4 and square root 70.4. That give me 8.39 radian per second. But we want to find a kinetic energy, right? So we have an equation over here. This is the kinetic energy. So that will be 1/2 moment of inertia, 1.25 kg meter square, multiplied with, well, actually, I just going to multiply the omega square, which will be 70.4. And when you multiply this together, then you got 1.25 divided by 2 times 17.4. Then I got 44. So that will be how you can calculate the kinetic energy of the rotation and understand how you can use the definition of the torque and the definition of the kinetic energy for rotation to find the solution for this example.